So welcome to day 3 of counting and probability. Today we're going to look at some different strategies for counting.
Okay, first we're going to do a homework review. So
Okay, so first problem, type your answer to that in the chat.
okay, I see one answer in chat. Does anyone else have an answer to number 1? Again, it's just the answer from your homework. Okay, I see 2 answers. Did anyone else do the homework? Okay. So the answer to number 1 is 108. Okay. So 6 factorial plus 5 factorial plus 4 factorial is going to equal 864. And then 864 divided by 8 is going to be 108. So the first one is 108. Number 2, how many ways can the letters in the word combo be arranged?
So you guys are correct, the answer would be 60. So for these types of word questions, basically the total number of ways to arrange it would be like the number of letters and then find the factorial of that. But then you also have to account for like repeated letters that can be swapped around and still get the same kind of word. So then we do 2 factorial since there's 2 O's. And then our answer is going to be 60. So good job. What did you guys get for number 3? All right, so it looks like number 3 was probably kind of a confusing problem. So let's go through it. Basically, we're going to write out like 4 time slots like this, where this one's the earliest, and then that one's the latest. Okay, and then we're gonna figure out every case basically. So we're going to put, we're gonna use T to represent tennis practice. So say we go to tennis practice first. If we go to tennis practice first, using what's in the question, what has to be after tennis practice? What has to be in the second slot? Yeah, that's right. This has to be homework. It can't be laundry or cleaning the room. We're going to do cleaning the room as C and then laundry as L. Okay, so then once you have this, you can either go like C and then L or L and then C. So that's two possibilities. And then now let's see. Okay, so if we put T right here, then again, H has to follow T, and there's another two possibilities. And then say we put T over here, so then this one has to be H. Okay, so that one has to be H, and then that's going to be another two possibilities. Okay, but then finally, all right, oh, never mind. So this one doesn't exist, sorry, because we can't put your homework last. Okay, so ignore that one. And then say we're going to put tennis last. Okay, and now this one, the other three can be put into any of these slots freely. So that's just, so that's just like, so there's three options here, times two options here, times one option here, because you could put like home H, C, or L in this slots. And yeah, so that's going to be 6 possibilities for this one. And then we just add up all of the cases that fit our criteria. And that's going to give us 10 possibilities. Yeah, exactly.
Okay, what about number 4? What did you guys get for that one? Let's have like at least 2 more answers for this one.
There's a little more than 8.
Okay. I see like a couple of answers, but I'm guessing everyone else is kind of stumped. So if you first try to like actually count each of the triangles, like 1, 2, like that, it's gonna be really hard, and you're probably gonna like end up spending a lot of time on this question. So what you do instead is, so you know that in order to make a triangle, you need to have 3 points, right? And so you just do, there's 9 dots, so 9 choose 3. To see how many different like possible combinations of 3 dots you can pick from this grid. And then you have to make sure that you are subtracting some of these combinations, because like this would be an example of 3 points, these 3 points right here. And if I pick these 3 points, it becomes a line instead of a triangle, right? So then I have to account for those. So there's 1, 2, 3, 4, 5, 6, and then also these diagonal ones, 7, 8. So I have to subtract 8 from this. So then, oh, oops, that is a really weird 8. But yeah, so 9 choose 3 is what? So that would be 9. Oh, 9 times 8 times 7 over 3 times 2, because the rest of it cancels out. And then you just simplify. And this gives you, what is it? 84, but minus 8, you can't forget about that. So then you get an answer of 76. Does that make sense to everybody? Okay, that's good. No, this one is kind of hard at first, but once you like do it once, oh, sorry for erasing the answers. It's like much easier. Okay. And what about number 5? What did you guys get for that one? Let's have like at least 3 people answer, because you guys should have all done your homework like yesterday. So it's okay if your answer's wrong, just like, participate. Unless you were stuck and didn't have an answer, then that's okay. Okay, well, I guess I'm just gonna assume this one was harder too. So for this one, you need to have 3 boys and 3 girls, right? And there's 9 boys and 8 girls in the class. So in order to just look at the boys and the girls separately, the number of possible combinations of boys would be just 9, choose 3. And the same thing for girls, so 8, choose 3. That's just like the number of groups of 3 people you can pull from both of these groups. And after you get like those 2 combinations, all you have to do is just multiply them. Since like each of these groups can be matched with each of the groups in the second, like each of the groups of boys can be matched with each of the groups of the girls. So then once you just multiply, your answer should be 4,704. Yeah, good job, Charles.
Okay, so does anyone have any questions about the homework before we move on? Oh, you added them.
Oh, you added them. That's sad. But yeah, that's like a common mistake.
Remember the fundamental counting principle. You have to multiply, be independent of it.
Okay, so today we're just going to learn about some different types of like counting and probability. So handshake and team problems, table and bracelet problems, complementary counting, sticks and stones strategy, and then line path problems and strategies. So today we're not going to learn like a lot of new content, but we're just basically going to learn to apply some of the concepts you've learned to common types of counting and probability problems.
Okay, so one common type of problem you might see are like handshake or team problems. So using this example, you'll see what I mean. There are 10 people in a room. If each person shakes hands with each other person, how many handshakes will occur? So we're going to go over a few different ways that you can approach this problem. So this first one is probably like the easiest to understand, but also probably the slowest. So the first person is going to shake hands with everyone except for himself. So he's going to shake hands with 9 other people. You can see here, he's going to like have a connection to each of the others, and there's going to be 9 connections. Okay, and then the second person is going to shake hands with everyone except for the first person because the first person already shook hands with the second person. And so he's gonna shake hands with 8 other people. And then so on and so forth. So third person is gonna shake hands with 7 people all the way down to the 10th person shaking hands with no one because everyone already shook hands with him. So the total number of handshakes would just be 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, which gets you 45 handshakes in total.
So the second method is we're first gonna go kind of simple, and we're just going to assume that everybody will just shake hands with every other person. So that means that each person shakes hands with 9 other people. So then there's 10 people, so you just do 10 times 9. And then, but if you do it this way, then it means that like the first person shaking hands with the second person, and then the second person shaking hands with the first person, that's going to be counted as 2 different things, although they're actually the same thing. So each handshake is actually counted twice, which is why we would divide by 2 after this. So the general formula, you're going to see this again, but it's just the number of people times the number of people minus 1, and everything divided by 2.
And then the third method to do this is thinking about it with combinations. And the way you think about it with combinations is that you choose 2 people out of the 10 to do a handshake. So 10 choose 2 is equal to 10 times 9 divided by 2 times 1, which is equal to 45.
Okay, so you can also apply this to team problems. In a certain league, every team plays against every other team exactly once in a tournament, and the team with the most wins is the champion. If the league has 16 teams, how many total games will be played? So go ahead and try and solve this, and you can also type what strategy you used in the chat. Whether it's the first one where you add it, or the second one where you use the formula, or the third one where you use combinations. Yep, so 120 is correct. So the strategy we see here on the screen is going to be the addition. So the first team is going to play 15 other teams. Second team is going to play 14 other teams, and so on. So you add all of them up and you get 120 games. And I see most of you saying that you're going to use the second strategy. So that's just n times n minus 1 and everything divided by 2. And n here would equal 16 because there's 16 teams. So 16 times 15 divided by 2, like Charles says in the chat. And then you can also do combinations like 16 choose 2.
So yeah, this is just like another reminder. So for handshakes and the team tournament ones, you can use this formula. It's pretty simple to understand.
So now on to table and bracelet problems. So our first question, Alex, Barry, Celia, Dwayne, and Esther need to pick seats around a round table with 5 seats. How many distinct seating arrangements are possible? So let's have Alex pick his seat first. How many choices does he have? Okay. It's not actually 120 again. Okay, 24. Do you know why it's 24? Well, that's not necessarily how it is. But so Alex picks his seat first, so he has 5 choices. All right. And then there's 4 choices left for Barry, and then 3 for Celia, and 2 for Dwayne, and then 1 for Esther, right? That's going to be 5 times 4 times 3 times 2 times 1 is 120 total seating arrangements. But there's a problem with that. When you rotate the table, the seating arrangements are all still going to be the same. So that means that you have to divide by the total amount of rotations you can do, which is going to be 5. 120 divided by 5 is 24. Yeah.
Okay, so let's do some practice with this. How many ways are there to sit 6 different people around a table? Yeah, so the answer here is going to be 120. So we're going to do 6 factorial first, but then we also have to divide that number by 6 to account for rotating, because each person can like rotate around in 6 different positions. And so that's going to be 6 factorial divided by 6, or 120. So nice job.
Okay, next we're going to look at bracelets, which is pretty similar to tables. So Alice has 5 different colored beads that she wants to put on a bracelet. And this question is asking how many different bead arrangements can she make? And so I saw an answer that said 24 in the chat. So if we just think of this like the table problem, the first bead, like the red bead, has 5 choices, the second has 4, and so on and so forth. So, and then you divide by 5 to account for the rotations. So your answer would be 24. But it's actually not correct. So this is because this is a bracelet, right? And you can just like pick it up and rotate it or flip it around if you want. So if you look on the left, those 2 bracelet arrangements are actually the same, since if you flip one, then it's the other. So now we have to divide by 2 because for each arrangement, you can just flip it over to get the same one. But you're actually counting them as 2 different ones right now. So in addition to dividing by 5, you also have to divide by 2. So for this one, the answer would be 5 factorial divided by 5, also divided by 2, which is 12. Yeah. Yeah, maybe they're big beats.
So a quick summary on tables versus bracelets. Remember, so both of them can be rotated. Both tables and bracelets can be rotated. So you have to divide by the amount of rotations you can do, which is also just like n minus 1 factorial. And then remember that a bracelet can be flipped. And I don't think that in real life you can flip a table. So since you can flip a bracelet, you have to divide by 2 because there's going to be symmetry associated with the flipping of a bracelet.
All right, so let's do some more practice with these problems. I'll put the link in the chat. And so then just go to slide 2. Okay, so the first problem, in the Big N, which is a middle school football conference, each team plays every other team exactly once. If a total of 24 conference games were played during the 2012 season, how many teams were members of the Big N conference?
Yeah, I can write the formula on the Jamboard.
So we'll wait a few more seconds to see if anyone else wants to contribute an answer. Okay, so yeah, you guys are right. The answer here is going to be 7 teams. And Aryan, since you're the first to put an answer, do you want to walk us through like what process you used to find the answer?
Or so basically I used the formula, I did it backwards. So it would be 21 times 2, which is 42. So it's now n times n minus 1. And I know that 7 times 6 is 42, and 6 is 1 less than 7, so I knew it's 7.
Yeah, that's perfect. So you multiply both sides by 2, and then you think about like the multiples of 42. That would, you can just do 7 times 6. So here 7 is going to be n. And then you can also go back and check like using the addition method or something if you wanted to. And then you're going to get 21 total conference games. So good job, good explanation.
Oh, that's a long question. At a twins and a triplets convention, there were 9 sets of twins and 6 sets of triplets, all from different families. Each twin shook hands with all the twins except his or her siblings, and with half the triplets. Each triplet shook hands with all the triplets except his or her siblings, and with half the twins. How many handshakes took place? This one requires some understanding of how the handshakes work. I've seen this problem on Alchemist. I think they got the problems from Alchemist. Okay, well, I see two answers, and they're kind of different. So
Okay, so Aryan has the correct answer. This is 441 handshakes. So let's look at how to tackle this problem. So there's 9 sets of twins and 6 sets of triplets. And so if there's 9 sets of twins, well, each twin, there's like each pair of twins, there's 2 of them. And so that's 18 total people. And then 6 sets of triplets, that's 6 sets of 3. So that's also 18 total people. And now each twin is going to shake hands with all of the twins except his or her siblings. So, and they're not going to shake hands with themselves. So their sibling plus themselves, that's 2 people they're not going to shake hands with. So they're going to shake hands with like, let's say 16, right? And so then personally, I did this problem with like the addition method, I believe, and I was just adding everything. Okay, so the first one is going to shake hands with like 16 people, and the second one is going to shake hands with like 15 people, and so on and so forth. And then so now if we look at the triplets, so each one is going to shake hands with all of the triplets except their siblings, and with, oh, sorry, we forgot about half the triplets. So they're going to shake hands with half the triplets. Then that's going to be 9. Okay, wait. I think I'm doing this wrong. So each one is going to shake hands with half the twins except their siblings, and they're also going to shake hands with like 9 of the triplets. And then so each triplet is going to shake hands with all of the triplets except for their siblings. So they have 2 siblings here, and so they're going to shake hands with like 15 people plus 9, which is half the twins. So then that's, so we have like a 24 handshakes. And so using like, we can also use like our n times n minus 1 formula, but it's going to be a little bit different here. So there's like 18 twins, right? That's our n. And then we multiply that by 25 because we add on the 9 triplets they're going to shake hands with. Then we divide that by 2. And then you add that to the triplet handshakes. So then that's going to be 18 times 24 because they have like 2 siblings. So you remove like 1 extra sibling, divide by 2. And I think that should equal like 441.
Okay, Mary has 1 red bead, 1 green bead, 1 yellow bead, and 2 blue beads. She wants to make a bracelet with these beads, and how many different bead arrangements can she make? So remember, a bracelet can be rotated and flipped. Okay, I'm gonna wait for like one more answer. I see a 5 and then a no, wait. Okay, I'll just go for it. I think I saw the right answer, but then it was like gone. So the right answer is actually 6. So this is because first we look at these 5 beats, right? So there's 1, 2, 3, 4, 5 beats. And so the number of arrangements you can do, just like not counting for rotations or flips yet, is just 5 factorial, which is 5 times 4 times 3 times 2 times 1. And now we have to account for some of these things. So for the rotations, you know that since there's 5 beats, there's going to be 5 different rotations for each arrangement. So we divide by 5. Then we know it can be flipped, right? So then each arrangement can be flipped once. So that'd be 2 different arrangements that are being counted as 2 different ones when in reality they're just the same one being flipped. And we can't forget that there's actually 2 of the same beats here. So these 2 blue beats were being treated as 2 different beats, but in reality, you can't actually tell these apart. So now you also have to divide by 2 once again. So now if we just calculate, we get 3 times 2 times 1, which is 6. Yeah, I thought I saw a 6 at first. So basically you just do the normal bracelet method, but account for the 2 beats that are the same. Yeah, good job if you got 6.
Okay. At a gathering of 30 people, there are 20 people who all know each other and 10 people who know no one. People who know each other hug, and people who don't know each other shake hands. How many handshakes occur? Keep in mind what the question is asking. It's asking for the amount of handshakes. Okay, so the answer here is going to be 245. And you can think about it kind of as cases. So 10 people, so they're asking for the amount of handshakes, and there are 10 people who don't know anyone. So those 10 people, they don't know anyone. So 10 times 9, or like 10 times 29 divided by 2, right? Because there are 10 people and they don't know anyone, so they can't shake their own hand. So 10 times 30 minus 1, or 10 times 29 divided by 2 is going to be 295 or 245. Wait, what? 1 second.
Wait, so actually what you would do is,
Dude, I'm so
for
bad
the
at counting and probability.
okay, so the 10 people who know no one, like within the group of people that know no one, they're all gonna shake each other's hands, right? So then that means it's just gonna be like 10 plus 9 plus 8 plus blah 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 blah. So 10
Wait,
times.
never mind. I got it.
You got it.
Yeah, I think it's 145 actually.
No, the answer is 245.
All right, never mind. I'm kind of bad at this.
Okay, so you do 10 times 9 divided by 2. So then you get 45, right? And this is within the group of people that don't know anybody. And then each of the 10 people that know no one will also shake hands with the 20 other people that are in the other group of, like the other group, the group that all know each other. So then that'd be 45 plus 10 times 20, because each of these people would shake hands with the 20 people. So then it's just 10 times 20, which is, what is it, 200, plus 45, which is 245. Does that make sense to everyone? Okay, I'm gonna assume it does, because some of you got the right answer.
Okay, so let's go back to the presentation. And so next we're going to cover complementary counting.
So complementary counting is basically when you're solving problems, sometimes it's like actually easier to find the opposite of what the question is asking for. So what this means is basically, we're going to look at it a little more in detail with an example, but so you can just find the opposite of what the question is asking for, and then you kind of subtract it from the whole to find the actual answer. Okay, so for example, in 5 flips of a coin, in how many ways can at least one head be flipped? So what is the opposite of what this question is asking for? Okay, so I see at least one tail be flipped. That's like, I see how you would think that would be the opposite, but it's kind of, at least one tail being flipped is kind of the same thing, because like there's only 2 sides to a coin. And so I kind of want you to think about it like,
It's kind of like what the question's asking for at least one head. So what would be something that you can count that, yeah, it's like 5 tails or something, right? Something you can count and then subtract from the total so that you get at least one head.
We're finding like something that does not fit the criteria of at least one head.
so yeah, what you're saying, Charles, 5 tails, or which would be just no heads at all. So that would be the opposite thing we would count in this situation. So no heads is the same thing as 5 tails. So, and then we would just find how many ways you can flip no heads, and then find the total number of ways to flip any number of heads. So just like the total amount of possibilities, and then you subtract the number of ways to flip no heads from the total. So yeah, and if you look at this, you can know that the opposite of what we want to find is actually much easier than finding what we want to find. So yeah, and like you said in the chat, there's only one way to flip no heads. So you just subtract that from the total number of ways, which is 32, to get 31 ways to flip at least one head.
So why should we use complementary counting, and why are we learning it right now? Well, so in that problem, if we didn't use complementary counting, we would have had to find a whole bunch of different cases. Ways to flip one head, ways to flip two heads, ways to flip three heads, all the way to ways to flip 5 heads. And then we would have to add all of those up. But our complementary counting strategy just takes a few steps because there are fewer cases that like don't fit the criteria, and there's a lot of cases that do fit the criteria.
So Jasmine rolls 3 dice, and then she adds up the numbers on the top faces of the dice. And how many ways can she roll a sum greater than 4? Think about how you can make a sum greater than 4. It's asking for some greater than 4. So 4 is not greater than 4, remember. So you can think about the amount of ways. 112 is another possible way, right? She wants to roll a sum greater than 4. Yeah. So it's going to be 212 because of what Aryan said, right? There are 3 ways that you can roll, like 112, 121, and 211, and then you can roll 1, 1, and 1. So those are like the 4 ways, or like the 4 exceptions that don't work. So you can subtract that from the total of 216. And so then you get 212, because 6 times 6 times 6 gives you the total amount of possibilities, which is 216. Are there any questions about that? Complementary counting is just essentially counting what you don't want and then subtracting that from the total. And usually in many problems, you're going to see that counting what you don't want is way simpler than counting what you do want. And complementary counting, I use complementary counting a lot. Right? Because sometimes counting what you do want it's really complicated. There's multiple different cases you have to consider, and in those cases, there's even more cases. So complementary counting is really useful. I think we can go on to the next slide if no one has any questions. Oh, it's our 5-minute break.
If you have any questions, you can ask us right now, or just come back to your computer after 5 minutes.
It's not letting me exit this. Okay, give me a second. Okay, that's really weird. So moving on, we're going to learn a strategy called sticks and stones, which will be really useful when you see problems that ask you maybe to organize objects or distribute objects like among a group of people or like some containers. So you might have heard of this also called stars and bars. But so let's look at how this might work. So for example, Jordan is going to try to distribute 10 identical pieces of candy to his 4 friends. And how many ways can he distribute the candy? So to solve this problem, what would you do? These are great answers, everyone. So let's see what strategy, how we can break down this problem into a simpler way. So here are Jordan's 10 pieces of triangle candy, and here are Jordan's 4 friends. So we're going to try to group the candy between them. So this blue guy is going to get 2 pieces, orange guy is going to get 4 pieces, green guy gets 3 pieces, and then I guess that's dark orange guy gets only 1 piece. But a better way to do this instead of circles is going to be lines. So you should note that we're going to need 3 lines to divide it up among 4 people. And so why are we using the lines instead of circles? Well, with the lines, you can easily adjust who gets how much candy. So say we're going to do this. First person gets 3 candy, second person gets 2 candy, third person gets 5 candy, and poor little guy in the end, he has no candy. All right. But you can also even do something like this, where this one guy gets 10 pieces of candy and everyone else is sad. Where you have the 3 sticks on the end and then the 10 candy in front. So now what have we done? Well, we have just changed the problem into how many ways can we arrange a line of 10 candies and 3 sticks, right? That's what we've changed the problem into. And so in total, we're going to have 3 object positions. And then the position of the 3 sticks determines which friend gets how many candies. So to solve this, we're going to do 13 choose 3 because we can just figure out like how we're going to position the sticks within this to divide the candies. And so we're going to get 286 total ways for Jordan to distribute the candy. So 13 total objects, 10 candies plus 3 sticks, and then we're going to figure out how to distribute the sticks.
I think you divide by 3 times 2 times 1 because when you divide up the candy, some groups, like 6 groups, will be the same, right? And that's why it's choose 3. So you need to divide by 3 times 2 times 1 since you're overcounting. I don't get why there's 13 positions because the 3 sticks count as positions as well. Right, because the 3 sticks, they divide up the 10 candies into 4 groups. So they're like placeholders kind of. And so then it's like 10 plus 3, choose 3. There's like a general formula for this, but I don't think it's good to memorize it unless And I think it's better if you just understand the concept as a whole, because once they start adding like tricks into the question and something that you haven't seen before, if you don't actually understand how sticks and stones work, you probably won't be able to use this correctly in the question.
And so what if Jordan is actually a nice friend and wants to give each of his 4 friends at least one piece of candy? So if this happens, then we'll just, like, it's pretty simple. So what you do is just remove 4 of the candies, because we're just gonna assume he already gave them out to each of his friends. So then now we only have like 6 candies and then 3 sticks. So that's 9 objects in total. So yeah, somebody said in the chat 9 choose 3. And yeah, so that's what you would do now. So you would just do 9 choose 3, which would be 84. So when like they say you're giving at least one piece to everyone, or like at least however many pieces to everyone, you just kind of remove that part of your object and just account for them as being gone already. So does everybody understand how like sticks and stones work? Okay, yeah. So the sticks become objects themselves. So they actually take up like a position, basically.
Okay, so you try. Now Walter needs to sort 16 identical jars into 3 different boxes. If each box needs at least 1 jar in it, how many ways can Walter sort the jars? Wait, is 286 your answer to this question? It says that each box needs to have at least 1 jar in it. Right. Okay. So someone who got 455, did they want to show their work and explain how they got 455?
I can.
Yeah, sure. Go ahead.
All right. So this one, it's so each one has to have 1 jar. So you take away 3 of them. So now there's gonna be a 13, and there's 2 sticks for 3 different boxes. So you add 2, and it's 15. Choose 3.
15 choose 3.
Yeah, if that makes sense.
Okay. Yeah. Okay, so your approach and everything was right, but are you sure it's 15 choose 3?
I'm fairly sure.
Okay. Well, when you do 15 choose 3, all right, so this is the way that I think about it. So we can like draw like, or we can put 16 jars, and we can, would it be 16 choose 3? Okay. It would be 15 choose 2 actually, I think. And so the way I think about it is 16 jars, and I need to put 2 different placeholders, not 3. I need to put 2 sticks because 2 sticks will divide it into 3 different groups or 3 different boxes. Can someone like draw or like draw the 16?
You want me to draw 16 jars? Okay. You can draw them as rectangles. Okay, I'm only going to draw 13 jars then. Should I draw 13 or 16?
No, draw 16 because I think it's easier if they think about it this way. And
Okay, that's 16.
okay, so the way that I think about it is that there needs to be at least 1 jar in each box, right? So I think about how we can place the 2 sticks that make the 3 groups. I think about how we can place them in between the jars. So there's 15 total spots in between the jars that you can place the sticks. And so then it just becomes 15, choose 2. 15 spots in between the boxes, and you choose 2 to put the sticks in. Right, so then it becomes 15 times 14 divided by 2, which is just 105. Yeah. Does everyone understand how it's 15 choose 2 instead of 15 choose 3? I need some encouragement in the chat. Okay.
Yes.
All right. Yeah. So the main part was that 2 sticks make 3 groups. 3 sticks make 4 groups. Right. So that's next question. Or okay, review.
All right, so to review, you're going to try to sort M objects into N groups. So how many ways are there to do this? Well, so if you're dividing something into N groups, you're going to need N minus 1 dividers. So that's why the N minus 1 is there. So if you're doing 3 groups, you need 2 sticks, okay? And so then for the first part, we're trying to find the total number of objects. So there's going to be M objects, and there's going to be N minus 1 like sticks or dividers, right? So we add them together to get the total number of objects. And then we do that number, choose N minus 1, or that's going to be the number of dividers. So basically the total number of objects plus dividers, choose the number of dividers, if that makes sense. And so remember that choose indicates that this is going to be a combination. So like the order of the objects, all the candy is identical, so it doesn't matter.
Okay, we're going to go to the Jamboard and do some more problems now. So go back to the same link. So now go to slide 7. So 3 dice are rolled. How many ways are there to roll a sum of 6 or greater? So we're kind of going back. So this one isn't a sticks and stones problem. This one is the complementary counting one. So try to remember how to do that. You just find the opposite first. And once we get like a couple of answers, I might like try to call on some of you to explain how you got your answer if it's correct. Okay, I'll wait like 1 more minute.
All right, how about we kind of do a hint. So for these types of problems, there's going to be like a total. This is the total number of ways you can roll 3 dice, like the total number of combinations you can make. And so okay, wait, I'm not going to do it like that. So we're going to divide this into like 2 categories. One is what we're trying to find. How many ways are there to roll a sum of 6 or greater? And then what is going to be on this side? Like what does not fit the criteria? All right, does anyone know what would not fit the criteria? What would like be the opposite of that?
5, 4, 3, 2, 1.
Less than 6?
Mm-hmm.
Yeah, exactly. So this is going to be like 1 through 5. Let's write 1 through 5 there. And so if you find the total, so this whole circle, and then you subtract away the 1 through 5, then you're going to get what you're looking for. So you have to find how many ways there are to roll 1 through 5, basically.
Okay, so I see a couple of right answers, and I think the hint to help you guys. So, does anybody want to like explain how they got the right answer, which is 206? If we have a volunteer, they can. Yeah, could you do it then?
Okay, so first there's one way to get 3, so it's 216 minus 1. And then to get 4, you could do 1, 1, 2. And there's 3 combinations for that. Since 2 could be in any of the 3 places. For 5, it could be 1, 2, 2, and the 1 could be in 3 places. Or it could be 1, 1, 4, and the 4s could be in the 3 places. So that's another 6 you subtract from it. So that is, and then 6 counts, so you wouldn't subtract 6.
Yeah. Did you say 113?
Yeah.
Oh, okay. So this one also goes to 5. So there's what, 6. And so I think he said you just do 216 minus this 1 plus 3 plus 6, which is 10.
Yeah.
So you would get your answer up here. Yeah, that was a great explanation. Good job. So I think, I hope everyone gets that. You're just counting the easier part, basically, the opposite of the answer, because it's much easier to count. And then you just subtract from the total amount.
There are 3 dice. One dice has the first 6 positive integers, the second one has the first 6 positive even numbers, and the third dice has the first 6 positive odd numbers. How many ways are there to roll a sum greater than 6? So again, I think complementary counting would help here. Because if you don't use complementary counting for these kinds of questions, you're going to have to count the how many ways to roll a sum that's equal to 7, and then you're going to have to find that all the way until 216, and then you're going to have to add the probabilities of all those different cases together. So I think complementary counting is what you want to do here. Also, remember that 6 is not greater than 6. I think I'll wait for a few more answers. Okay, so 2 people have the answer of 201. Does anyone else have an idea of what the answer could be? Remember, for this question, you're just going to count the number of ways you can roll a sum less than 6. And there aren't that many ways that you can actually do it. So okay. So the number of ways you can roll a sum less than 6, you can roll the numbers 1, 2, and 1. You can roll 2, 2, and 1. You can roll 1, 4, and 1, because remember 6 is not greater than 6. So those are 3 ways that, and so there are 216 total ways that you can roll. There are 216 total possibilities. Oh yeah, there's also, oh wait, there's 1, 2, and there's 1, 2, 3 as well. So 216 minus 5 is 211.
Okay. Yeah.
But it doesn't say what order you roll the dice in.
Yeah.
You could have rolled like the third one first.
But
It
you
just-
also could have rolled
That's why you can just rearrange the numbers and get 3 times more. So it should be 15, right?
Yeah.
I think we just care about the sum and not really
Yeah,
the order the numbers come in. We just care about what sums there
yeah.
are.
The reason, yeah,
But it says how many ways are there to roll a sum.
yeah.
I'm gonna still stand by my answer.
The reason I don't think that you can, the reason that you can rearrange the sums in dice before, and like the dices before, is because they have the same numbers on them, right? So you can roll them differently, I guess. because they have the dice, like when you have 3 standard dice or it's three standard die or whatever, they all have the numbers 1 through 6. So you can roll like a 3 2 1 and a 1 2 3, but here you can't do that because the die here have different numbers on them. And the only way you can roll like the same thing, I guess, again, or like twice, is 1 2 3 and 3 2 1, because like you can't roll a 1 4 1 twice, because you can't have a 4. You can have a 4 in the first one, but you can't have a 1 in the second dice, or a 1 in the third die.
So you specifically have to roll the first one first, the second one second, and the third one third. You can't roll the second one first or the third one first.
I guess so.
So
Yeah.
basically, like, what
Because
we're
if you
doing
could
here-
roll them, in like a different order, I guess it would be 6 times 6 times 6, right? But then it would be like times another. It would be times like 6 factorial again, because you could choose one of the 3 die to roll first, and then one of the 2 die to roll second, right? So the order there doesn't matter, because at the end of the day, you're just rolling the 3 dice. Yeah, I think this question may have been a little confusing.
Does that make sense why we're doing 216 and then 5? Because like it's 216 because there's 6 numbers on each of the 3 dice, right? And like the sum, this 216 is counting like the possible combinations of like possible outputs of the 3 dice, and like there can be numbers that add up to the same number, like 1 2 3 and 3 2 1, but our total number is also counting them as different things. And while we're counting the 5 like sums that are less than or equal to 6, we're also counting them as different things. So like 1 2 3 and 3 2 1, we're counting as 2 different sums. So that's why we can just subtract 5, because both our total number and our like sum that we're finding are talking about it in the way where sums that are the same but are consisting of different numbers are counted as 2 different things. So that's why you can just subtract 5. Like if you, as long as you are counting the same way both times, you can just subtract. That might have been a little confusing, but like that's how it works.
So like, for example, like you guys multiplied 5 by 3, right? But then you can't even do that here because like say this one is 1 4 1, but only 2 of the dice have 1. So you can't like do 4
Yeah.
1 1. That's like not possible.
Yeah, the only reason you could do that
But dice.
before was because the 3 dice had the same numbers on them. So you could roll the same number, but like different. You could roll the same combination, I guess, but you could roll it differently, with like a 4 in the first die and then a 1.
Oh,
a 1.
okay.
Yeah, but you can't do that here because the numbers don't have the same because the dice don't have the same numbers on them. The only like permutation, I guess, that you could roll like twice is 1 2 3 and 3 2 1. Right? Does that make sense?
Okay. So perhaps we'll just move on to sticks and stones problems here. So how many ways are there to sort 8 identical stocks into 3 bins?
Remember, the question doesn't specifically say that each bin has to have a sock.
Okay, so let's see. We have 8 socks, and we're trying to divide them into 3 groups. So how many dividers, how many sticks will we need here? Anyone? You can put in the chat.
2. You need to have 2.
Yeah, exactly. So we're gonna have 2 sticks. We can just draw the sticks right here. And now, so how many total objects do we have?
8.
Well, like, okay, objects plus dividers, because we're counting the sticks as objects.
Oh, then it's 10.
Yeah, perfect. So we're gonna have 10 objects. And so that's gonna be like the first part. So we're gonna do 10 choose and then the number of dividers, which is actually like this
3.
doing 10 choose the other way around, but okay. So we're gonna do 10 choose the number of dividers. 10 choose 2, which equals 45. So there's 45 ways to sort these socks. Basically, in these problems, just think about how many dividers you're going to need and add them as objects to like your, you can even draw them if you want.
And make sure at the last step, when you're doing like the number of objects, choose the number of dividers, that you don't go back to the 3 bins. You have to look at your sticks. So there's actually 2 sticks instead of 3 like bins. So, okay, our next one is pretty similar, but this time each bin needs at least 1 sock. So maybe you might remember from our slideshow how we did something like this.
Wait, so we already do 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1.
Wait, I don't get, why would you do that? Hold on, there's, let's see, 1, 2, 3, 4, there's 8 socks, and you're just basically putting 1 in each of these bins. And remember, you just kind of think of them as gone. So you just throw away 3 of them, basically. You might be right, but I don't know what you're talking about with like the 7 plus 6 plus 5 plus 4.
Fine.
Okay. Okay. I see like 2 right answers. So the answer is actually 21. And so this is because we just like get rid of these, right? So wait, actually, hold on. I'm pretty sure you can move these. So we put the socks in here. And now we only are left with these 5 socks. And we still have 3 bins though. So now we still have 2 sticks on the side. So we have 1, 2, 3, 4, 5, 6, 7 objects. And we have 2 dividers. So remember, there's actually 2 dividers instead of 3. So we just do 7, choose 2, which is equal to 21, which is what I said. All right, and let's go back to the slideshow now. So we have like one more concept to cover today.
Okay. Line path problems. 1 second. All right. So how many paths are there from point A to point B if you can only move right or down? So what are some possible ways you can do this, like strategies? Yeah, so down 3, right 4. Okay, so that's one possible way. All right, are there any other possible ways? Down 2, right 4, down 1, right? That's another possibility. Yeah, but I don't think that counting does different possibilities. It'll take a really long time to do that. So what is something smart we can do? Or what's something we can notice about that? What if we designate going down 1 as D, as the letter D, and going to the right as the letter R? What is something you notice when you write out all the different paths? Okay. Something that we notice when we say that R is going to the right and then D is going down, it just becomes, the question just becomes, how many ways can we write, how many permutations are there when you're writing RR, when you're writing 4 R's and 3 D's? And that just turns into, so it just turns into like a name question. How many different orderings are there for someone's name, right? And then it just becomes 7 factorial divided by 4 factorial times 3 factorial, because it's 4 R's and 3 D's, right? And that's going to give us 35 paths. You guys remember do you guys remember from our last class how to do this question? How to do this kind of thing? Yeah. It's going to be 7 times 6 times 5 times 4 divided by 4 times 3 times 2 times 1, which is 35.
So yeah, basically for a grid with a width of n and a height of m, the number of paths from one corner of the grid to the other corner is n plus m choose n or m plus m choose m. So they're like the same thing. So you just like think of them as letters and yeah, kind of like a name.
All right, so now we have a practice question. In the following grid, how many paths are there from A to B such that you can only move up or right? This is almost, and we did this like just now, almost. The total number of moves is going to be 5, no matter what. Are you sure? I think the total amount of moves is going to be 7, because you can go up 2 and then to the right 5, and then you'll get from point A to point B. So I think the total amount of moves is actually 7. Okay. I'm going to wait for a few more answers in chat. Okay, so Charles thinks it's 21. What about anyone else? What do you guys think the answer is? By the way, I've been keeping track of points every time. So how many more slides do we have left? Today we have an 80 slide presentation and we're only at slide 50. So if we want to finish class on time, we need people to participate. But if I see more people participate, we ditch the remaining 30 slides and we do a Kahoot. How about that? Dang, it's not working. Okay. So there. Okay, so Hannah thinks it's 21 and Charles thinks it's 21. What about anyone else? Right. Oh, I think Aryan left. Okay. All right. Okay, so the answer here is going to be 21. And this is because there are 7. It's essentially just asking us how many ways can we order 5 vertical or 5 horizontal movements and 2 vertical movements. So it's going to be 7 factorial divided by 6, or 7 factorial divided by 2 factorial times 5 factorial, which is going to be equal to 7 times 6 divided by 2, which is 21. Are there any questions about this specific kind of example? Okay. Oh, wait, what?
Okay, so really quickly, we're going to cover a strategy to do weirder grids where that strategy is not going to work. So for example, this one, how many points are there from A to B? Well, you can't really use the normal strategy because the shape is weird and it's not going to have like a set number, not have a set sequence. So what we're going to do here is a strategy that involves like adding. So we're going to start at point A. And so basically we're going to write a 1 there. And from now, basically every subsequent vertex is going to be the sum of the vertex of the line that comes from the left or the one that comes from the bottom, because the direction we're going in, we have to go like up and to the right, if that makes sense. So this one, it only has 1 line there. So we're just going to add 1 to that. That one also has 1 because it only has 1 line going to it. So we're going to fill in all of these with 1s. And then this one is going to be a 2, this corner right here, because you add up 1 plus 1. Those are the lines that are connecting to it. These 2. Okay. And then now that one's going to be a 3 because 1 plus 2. This one's going to be 3 because 2 plus 1. And that one's going to be 4 because 3 plus 1. So what number is going to fill in this corner right here that I'm pointing at?
5.
Yeah, exactly. That's going to be a 5. Okay, so now we're going to go back over here. This is going to be a 6. This is going to be a 10 because 6 plus 4. And this one is just going to be 10 because there's no line connecting it right here. So that's not a possibility. We only count like straight to there. There's only one way to get to there. So then we continue filling in. And then this last point, that's going to be 16 plus 10, which is 26. And that is our answer. That's the number of paths we have. So yeah, 26 is the answer to this.
So we do have like 2 more Jamboard problems, but let's see. So do you guys want to do like 2 more problems that will help you and then do the Kahoot, or just go straight to it?
We'll take a vote. Either type Kahoot in the chat or type Jamboard in the chat.
And the Jamboard only has 2 more questions, so.
She's lying. There's 3 questions.
No, we're only gonna do the first 2 though.
Oh. Yeah. Okay, then then there's only 2 questions.
Okay, 2 people said Kahoot, 1 person said Jamboard.
Can we skip the rest of the slides? We didn't go over the binomial theorem yet, so we still have we have a lot more slides that we have to do.
So I'm seeing a lot of. Okay, well, not that many people are like participating, but you know what? Let's just go to the Kahoot. That will also give you some practice. So.
Yeah.
And you can do them on your own, Charles, if you want to. Okay. So yeah, the code is that 2372151.
I think today not Sai might actually lose.
I
There's
think
a
so too.
spider. There's a spider right next to my computer.
Nice.
Does the binomial theorem have anything to do with quadratics? Yeah, it has a lot to do with the binomials, actually. I don't know. Believe it or not, it does have a lot to do with the binomials.
All right, come on, guys. You voted Kahoot. Now join the Kahoot.
Dang. And there's supposed to be like 9 people joining the Kahoot. Actually, there's supposed to be like 10 people joining the Kahoot. I think not Sai is actually Sai.
What?
He's just
No
I think
way.
he's just lying about his name. See, because I remember Sai was telling me about it. And kids in my algebra class last week told me about it. They thought not Sai was a cheater.
All right, let's go ahead and just get started. Okay, if you want to join, you can also join in the middle.
Oh, I need to get set up. No, this is bad. I'm not ready. Okay, the answer here is 66 because it's going to be 12 times 11 divided by 2. Oh, wow, a lot of people got that one. Wait, there's only 5 people in the Kahoot. All right. I have to leave. Is that fine? That's fine. Okay, so remember, there's 9 identical gloves into 3 different bins. So we're going to have 2 dividers, and we're going to have 11 places where we can put those 2 dividers. So 11 times 10 divided, or 11 choose 2. 11 times 10 divided by 2 is going to be 55. Okay, so 9 identical gloves into 3 different bins. So going to be 8 places to put the 2 dividers. So 8 choose 2 is going to be 28. Because remember, each glove or each bin needs to have at least 1 glove. Or you could think about it where you give each bin 3 or each bin a glove, and then you can do the same method that you used last time. So it'd be 6 plus 2 choose 2, which is 8 choose. Oh, yeah, 8 choose 2, which is 28. This one's a little tricky. Okay, so the answer here is 10, and you can think about it, right? Like you give each bin 2 gloves automatically, so then that means that there's 3 gloves left, and you need to put 3 gloves into 3 bins, and so then it's 3 plus 3 minus 1, which is 5 choose 2, then 5 choose 2 is 10. Going to have 10 ways to put the gloves. See, it was blue. Like, you guys need to believe me. So there are 6 beads on bracelet, so there's 6 factorial ways you can arrange this beads, but then remember that you can rotate the bead, and each of those 6 rotations is going to give you the same ordering or like the same arrangement of the beads. So it would be 6 factorial divided by 6, which is 5 factorial, and then remember you can flip the bead. So you have to divide that again by 2, which will give you 120 divided by 2 is 60. Okay, so how many paths are there from A to B? Oh, I can't see the figure, but there are 5, but it's just ordering 2 down or 2 down movements and 3 movements to the right. So R, 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 D, D. So there's 5 factorial divided by 3 factorial times 2 factorial, which is going to be 5 times 4 divided by 2, which is 10. Okay, so mostly everyone's getting these questions right, which is good.
We're going to end the code a bit early once it reaches 11:29, so we won't get through all the problems.
Oh, wow. Oh, no, I'm too lazy to do this. I'm just gonna guess 12, guys. Not Sai might have gotten this question wrong. Oh shoot, it is 12. Okay. So, so let's do this the correct way instead of guessing. So there's one way there, and then I'm just gonna draw all the ones. 3 plus 1 is 4.
So that's how you do this.
Yeah. Remember, it's our secret counting strategy. By the way, Richard, Rusick, or like AOPS, they have really good videos about this on YouTube. So if you have time, you can watch those, and he explains it really well. Well, what is this? Yeah, I forgot already. Okay, this is great. I'm guessing 11. See, it was wrong. All right. Oh, wow, no one got it right that time. Yeah, it's the same strategy from last time.
So is this corner here? Okay, that's gonna be. Oh wait, I think we must.
I think it's 7 plus. I think 3 plus 4 is 7. So the one right there.
Oh yeah, yeah.
Yeah.
Wait, what?
Yeah, apparently you have the eraser out. Well, okay. I think this is 3. So this here is 3, then this would become 7.
Okay, I messed up there.
Then I'm not sure how this works here, but then this is 3, this is 3, and then 3 plus 3 is 6. Then 6 plus 7 is 13. I think the right answer is 13.
Yeah,
Okay.
that's the correct way to do it if you don't mess it up.
Yeah. Wait, who's second? Who's second?
Good job, guys.
Okay, put in chat if you were second place.
Just remember to do your homework for tomorrow's class. And you can do the extra Jamboard problems if you want to. It'll help you. So yeah, if you don't have any questions, then you are free to go.
Who is not Sai? I think Sai's lying about his name when he said it's not Sai. I'm pretty sure it's Sai though. Somebody keeps giving him the link.
Sai isn't even in the class.
Yeah, I know. Somebody keeps giving him the link. He's like really attached to the the introduction to counting and probability class because he taught it for the last 2 weeks. I don't know. We have to tell him to stop participating in the Kahoots. He keeps stealing everyone's points. Like at this rate, nobody's getting the gift card for the virtual cookie.
Bye.
Bye.
Bye, everyone.
Bye.
Bye.